Hello, good afternoon. You should hear me and you should see the desktop. Does everything seem okay?
Yes.
Yes. Okay, great. Thanks. Okay. All right. Got everything up. All right. I didn't get the homework assignment up there yet. You probably noticed that it's still not there. I've had so much stuff to be working on. I'm trying to get one more homework assignment that'll involve what we were doing with the end of ML. So, um, so I hope it'll be there in a day, maybe tomorrow. Okay. So trying to get all these homework assignments out for so many classes. So it's still not up there yet. Okay, so we're going to keep talking about higher order functions today, which is what the homework assignment is going to be about. The homework assignment is going to be a assignment about higher order functions. So we haven't really finished talking about them. So we still need to cover some of the things that I want to be in the homework assignment. So that's another reason why it's not quite ready. So today, uh, remember what we did last week is we did some more of these examples where if I give you a function type, you come up with a function definition that matches that type. This is good practice for reading and thinking about ML and thinking functionally, thinking in terms of what might you know, what kind of function would need this kind of type. These kind of homework assignments don't exist in C and C++ and Java. It makes no sense in Java for me to give you a type for a function and have you write the function. There's just a gazillion ways you could write any specific type. There's something about the way ML works, and Haskell's similar to this. A lot of times the type really restricts what you can do with the function anyway. So these kind of assignments actually make sense in ML. There aren't a whole lot of things you could do to give you that type, to get write a function with that type. So these are good assignments. They actually make you think in the way ML thinks. Start with a type and then come up with a function that matches that type. Okay. Now that's not the way real ML programming is done. ML programming starts with a problem. You know, write a function that does something, and then you come up with types. But this way of thinking is good practice. So this is a really good way to practice ML. So we're going to do a few more of these, and we're going to see that the ones we're going to do today lead up to some very famous examples. The examples in higher order functions that the book talks about: map and reduce. Okay, map and fold and reduce. So what I'll do is, I've already got it on my desktop. Do some more of those examples that are in here, and we'll see that we're going to do the later examples. They're a little bit trickier. Actually, they're not trickier, but they start becoming more interesting, and they start becoming closer to what we want, the examples that we really are most interested in. Okay, so look at an example like this one. Practice reading it. The grouping groups that and says that's a function that takes in an A and gives me back a B. So the function we're interested in, this arrow says that this is its first parameter. There's a second parameter up to that arrow. Then there's a third parameter up to that arrow. And then there's a return value, which comes after the last arrow. So the function has 1, 2, 3 parameters. The first parameter is a function. So here, I'll say, so the first parameter is a function. The second parameter is a function. So names like H and G are good names for functions. And the third parameter is a tuple of things. So I'll write that as an X comma Y. Okay, now the first function takes in A's and gives me B's. The second function takes in C's and gives me D's. This tuple is a C and an A. So this one's a C. Now that's the thing that can be fed into the second function. This one's an A that can be fed into the first function. Now what I want is a pair of DBs. Okay, D is what this function gives out, B is what this function gives out. So put it all together, and what you want is to take the first thing from this pair and feed it into the second function. Okay, But we have to get it lined up. Yeah. Well, let's look at what we do with x. X is that guy. That's the thing that's a C. The thing that's a C goes into the second function and gives us out a D. Oh, and that's what we want in the first item in the pair. So the output pair will be the second function applied to the first item in the input pair. Okay. The second function, which takes in a C, applied to the first item in the input pair, gives us a D, which should be the first item in the output pair. Okay. Then the first function applied to the second item in the input pair. So the first function applied to the second item in the input pair. The first function gives us out a B. That's the second item in the output pair. So done. That should be the definition. Okay, let me start up ML, and we can paste this into ML and see if we get the right type. Okay. Now it looks like, see, you can compare. Now this line of code will test it for us. What this line of code here does says F10 has type. You read this as Fn has type, and then here is the type that we declared up here. Now the compiler is going to check, does Fn have that type? If it doesn't, you get a compiler error. If it does have that type, the compiler more or less just says, okay. So rather than try to read that output, we can just ask the compiler, does F10 have that type? And it said, yeah, it had. It just repeats the type when the answer is yes. The type of F10 is that type there. If I goofed it up, for example, here's the definition of F10. Suppose I did this as H of Y, G of X. Okay, so I just applied, H was the first function, so I used H first on Y, and G was the second function, so I used G on X. I didn't pay attention to what I should have done. So suppose I do that one. Now check if it has the right type. See, and you get a compiler error. It no longer has the type I wanted it to. So if you don't have the right type, this line checks that this function has the type that we wanted it to have. So I just copied this type here to the right-hand side here, and then write F. See, this says a function of type this. Now here I said my function has type this, and the compiler checks it. So this is my way of double checking that I have the right type. Okay, so there's that one. This one's real similar. Okay, we've got a function h goes from a's to b's, and then another function, we'll call it g, that goes from a's to c's. This one takes in an a and gives me out a b. This one takes in an a and gives me out a c. Then I'm given an a, so I'm given an item. Okay, and then I want an output pair. So now I can write what the output should be. So I have this function, I call it h. This function, I'll call it g. This item, I'll call it x. This says give me the output, so that would be an equal sign here, saying now I'm going to produce the output. Now I need a BC pair. Okay, B is the output from the first function, so I need a pair. The B in the output of the output pair should come from the output of the first function. So I'll feed the first function x, and then the C in the output pair, C is the output of the second function, so I can feed it the x. Okay, so g of x. Okay, that should work. Okay, I can just copy and paste these two lines together. One line will define the function, the other one will test that it has the right type. Okay, no compiler error, so that was the right definition. Okay, again, practice in just reading. These arrows separate the parameters. The parentheses are grouping the error. Remember, if you drop the grouping, it doesn't become ambiguous. If you drop the grouping, it just becomes something very different. Now it's a function that takes in an A, takes in a B, takes in a function from A to C, takes in another A, and gives me out a B pair, BC pair. Now, I may not be able to actually do anything with this. You can write down types that have no reasonable definition. I don't want to try to figure it out whether this one does or not, but I can easily write for you a type. In a minute, we'll look at one. I can write for you a type pretty easily that has no reasonable definition. Okay, so if you take away the grouping, it completely changes things. By putting a grouping around this, you're saying that that input is itself a function that takes in A and gives me out B. So that's a function parameter to my function. And that's another function parameter to my function. So these are higher order functions. Okay. All right. And 12, real similar again. Okay. I've got a function as one input, call it H. A B item can call it X, and an A item can call it Y. And then we need a C item out. Well, what does this function take? This function takes an AB pair and gives me out a C. Well, I've got an A and a B. So here is an AB pair. Okay. No, I'm sorry. This is a B, that's a BA pair. If I need an AB pair, I need to reverse them. I have to pay attention real carefully. The function takes in an AB pair, but this parameter is the B and this parameter is the A. So if I reverse the order of these, that's a, that's an A, B pair. But I can feed that pair into my function, H. Okay. My function takes in an AB pair and gives me out a C, and that's what I want the output of the function to be. Okay, so I think that's the right answer, and I can check it. I'll do both lines at once. The definition and the line of code that checks it. Okay, see, passed. Okay, all right. Okay, let's do another couple more. Now, so we're just accumulating a variety of different things. Like here, the input the parameter is a function of a pair to an item. Okay, then I've got two items, and I can form them into a pair. So just you just do the natural thing. That there's probably not much else I could do with that type. This was an easy example of a function with that type. I don't know if I could really come up with another example. This is the interesting things. That's kind of an interesting type, and I really don't know if I could come up with another function that has that type. Boy, I don't think I could. Because you see, you're really restricted. Okay, you need a C item out. Okay, you got to produce a C item out. Okay, well, what are you going to cook this? You got to somehow cook up a C item. Okay, a B item and an A item by themselves aren't going to give you a C item. You don't even know what A and B are. You don't know what type C is. But over here, somebody gives you a function that takes in an A and a B and gives you out a C. So if you need a C item, try to feed this function because it gives you a C item. Well, what do you need in this function? An A item and a B item. Well, you have them. These are parameters. So there's really almost nothing you could possibly do other than take those two inputs and feed them into that function. Okay. So this is interesting. This is actually called theorems for free. This is actually a profound fact of ML that these functions have many types actually only have one way to implement them. Yeah, and for some very sophisticated reasons that this has been referred to as theorems for free. Yeah, and it's actually a fairly famous aspect of Haskell programming and ML programming. That if a lot of function types really only have one way to implement them. Okay, that means that that's actually kind of good. You could imagine that a compiler could generate this code for you from that function type. You can imagine that there's hardly, you can't write this thing wrong if there's only one way to write it. Yeah. So these are kind of like good things about the language, that the types of the functions put a lot of constraints on what you can do. And if you can build up your program out of lots of little functions, each of which can only be written more or less one way, your program sort of starts writing itself. And it's true in ML world that if you can figure out if you can break your program, if you can take a problem and break it into lots of little functions and figure out what the types of those functions are, that's usually what the design step is. Writing the code is usually then the easier part. The harder part is deciding what little functions does your program need. Build your program up out of lots of little functions and then write those little functions. Quite often, there's maybe only one way to write them, and then put them together the way you want to. Okay, let's look at another example. Okay, a function, call it h, another function, call it g, a pair of items. Okay, so use pattern matching. So there's a pair of items. Okay, now notice that this is one input parameter. See, I'm making really good use of pattern matching. I could have called that guy W. See, this is an input parameter, but there is no pattern. That input parameter is a function. That input parameter is a function. That input parameter is a tuple. So I write it W, but this is a lousy way to write it. I'm not making use of pattern matching. There's no pattern for a function, but there is a pattern for doubles. So I'd be better off writing this as, oh, an X and a Y in a pair. It turns out to be way better to use pattern matching when you can. So this should be written as a pattern, but it is one single. Now I could write it this way. In a minute, I'll do it. I'll write it that way, and you'll see that it's going to get ugly if I write it that way. Okay, now, so I'm going to write it as a pattern, then we'll go back and rewrite it as a item. Okay, so an H, a G, and a pair. Now I'm ready for the output. Need a B list. Okay. Okay, now let's see. I've got a C and an A item, and I've got a function from C to B and a function from A to B. Okay. Well, I could take that item and put it in that function and get out a B item. And I could take that item and put it in that function and get out a B item. And that's two B items. I can make them a list. So I can make a list out of the first function given now the first function takes in the A item. The A item is the second one in the pair. That's my first thing in the list. Okay, now I need another thing in the list. Well, I'll take the second function, the G function, but the G function takes in a C, which is the first item in the list. Okay. All right. Now let's check that this is right. Okay, no compiler error. Now, what's interesting about this one is not as constrained as the other ones were. Tell me another way I could write F13. See, look at real careful. See, there's kind of a simple little thing I could do. It's going to be a different function. It'll still have this type. What little bit of leeway do I have here? How can I take this? What could I possibly change here? There's one thing that I had a choice about. Remember, I want to B list out. Okay, that's a B item. That's a B item. Because see, that function gives me out a B item. That function gives me out a B item. I have to give that item to this function. I have to give that item to this function. But what is something I could have done differently? okay, I could change the names, F and K, but that's a real stupid change. Okay, changing the names of the variables is not a profound difference. Okay, this is not a different function. I think I got it right. That's not different. Yeah, I just relabeled the function, relabeled all the variables. In fact, instead of using G, let me use say J. Okay, so I didn't use any of the but that's not an important difference. Relabeling all the variables doesn't change the function. There is something I can do to change the function. So it really isn't quite the same function, but it still has that type. Has anybody seen it yet? There's one piece of leeway I really have.
Can you change the order of the list?
Yeah, change the order of the list. So go over here and redo this one. But instead of putting this guy at the front of the list, put him at this end of the list. So just change the order of them in the list. It's not a profound difference, but yeah, since the output was a list and there's two things I can put in the list, I have really no idea what order to put them in. I can put them in any order I want. Here's an interesting thing. Can I just ignore one of the, why do I have to have two items in the output list? Why not one? Does anybody, what do you think? Is that going to be an answer? It still produces a B list. Any opinions? Is that going to be an answer?
Yes.
Why?
It's still a list.
It produced a B list. Okay, now let's check. Is this a B list? Well, G is supposed to be a function from C to B, and this is supposed to be an item of type C. So I feed in an item of type C into a function from C to B, and I get out a B item, and I put it in a list. Okay, seems right. It's not right. This is not the right type.
Do you not know that H is a function now?
Yeah, because I ignored the H and I ignored the Y. ML says H isn't a function because you didn't use it as a function. Okay, so let's just check. Let's go here, give that answer to the, now this function's well defined to ML. There's nothing wrong with that function, but we'll see it does not have that type. Okay, so let's see that doesn't have the type we want. What happened to my ML? Did I close it? Okay, I must have accidentally closed it. Okay, so, well, I didn't get a compiler error. Let's, now look, it does not have two functions at the input. The H is not a function. The H is an A item. See, the H is an A item. The G is a function. Then I get a pair of a B and a D item, and then I get out a C list. Okay. Now, why did that type correctly? That I don't understand. I thought this would complain because, see, if I ask what F13, is, see, it has this type up here, which is not this type here. I don't know if somehow this type actually has that. I have to actually think. Types in ML are can be kind of tricky. It might be that in some sense to ML, this type is maybe a subtype of this type, and that's why it's not complaining. I didn't think ML did subtypes, but that's the only way I can think of that. It's somehow thinking that this type is not the type this is the type I got, this is the type I wanted, and they're not the same, but ML did not give me a compiler error like it did before. So all I can think of is that somehow in a subtle way, ML is thinking that this is somehow a subtype of this, though I don't really understand why. They differ in a couple different places. Oh, okay. I don't know. Yeah, it's not the type we wanted. Yeah. This one is not the type we wanted, but I don't know why this one's not catching the error. I don't understand why this one doesn't catch the error in that thing. But we can just see that it's not the right type. Okay. F13 has this type, and we wanted it to have this type. We wanted the first parameter to be a function. By not using the first parameter, ML just treated it as a thing of type A, not as a function from A to B. Okay. All right. So here we found an example where the type has a little bit of leeway. You have to cook up this output list. It doesn't matter what order you put the two things in. You can't just put one thing in the output list because then you're ignoring one of your input functions and then it actually isn't becoming a function. So you've got to use both of these, but it doesn't matter what order you put them in. Okay. All right, so this one is wrong. But I'm not sure why. Yeah, there's a question mark there about why that didn't type check quite right. Yeah, that's supposed to have checked the type for us. Okay, now let's do another one that's kind of, oh, now I said a minute ago that we should, what if you do this without using a pattern? So here's an ugly way to do this one. Function F13 takes in a function H, a function G, and a W. The W is the third parameter. Okay. Now, what I know I want to do for the output is I want to create a list. I want to take H of, well, I know that I'm supposed to take H of the second thing in the tuple. So that would be H of #2 of the tuple. Okay. Then I want to take G of the first thing in the tuple. See, X is really the first thing in the tuple. But if I don't use pattern matching, I have to write #1 of the thingy. Okay. Okay. Now ML is going to complain about this. Does anybody remember what it complains about this? We've done this a couple times before. ML is going to complain. Okay, think back. This is a tuple. We know it's a tuple, and we want the second thing in the tuple here and the first thing in the tuple here. There's an ambiguity here. Does anybody remember what it is that ML is going to complain about? We know something that ML doesn't know. Oops. Ah. Okay. See, ML didn't like something. What is it it doesn't like? This notation's ambiguous. This notation's ambiguous. So remember, what's ambiguous about that notation? What is that saying? This part here means what? Second item in a
Second item in the tuple.
top. Well, but what size is the top? Could it be the second item in a triple? See here, W, there, val, W equal 1, 2. Okay. What's the second item in W? It's a 2, right? But let W be a triple. And then take the second item in W. Notice that this means the second item not in a double, it means the second item in any tuple. The tuple can be any size. So you can have W be okay. There's a but, so that's a 6 tuple. And then you can ask for the second item in the 6 tuple. Okay. This notation doesn't say the second item in a pair, it's the second item in a tuple. Over here, ML doesn't know what size that tuple is. And that's what it complained about. We have to tell it now, since we're not using pattern matching, see, that tells it it's a pair. We have to say down here, we have to actually say it has type a C item and a, where is it? An A item. We have to tell it what the type of that pair is. So this is why ML really prefers that you use pattern matching. If you don't use pattern matching, it can't even always figure out exactly what you're talking about. So if I try to just say the thing W, I then have to tell it that W is a pair, not a triple, for example, and then this notation will work. Okay, it worked now. I had to, and if I get rid of that extra type declaration, then it doesn't work. So ML really prefers that you use pattern matching. It's very ingrained to the language that you should do things with pattern matching. So this function takes in 3 items, item 1, item 2, and item 3. There is no pattern for a function, so you just give it a name. There's no pattern for a function, so you just give it a name. But this item's got a pattern to it. The item is better called X comma Y. It's better called by its pattern than by just calling it W. Because if you call it W, then you have to deal with the fact that ML doesn't really know what kind of W you're talking about. Are you talking about a double, a triple, a quadruple? So you have to go back and tell it, well, W is really a pair. But if you're going to tell it that W is a pair, you might as well use the pattern. ML strongly prefers that you write code in patterns, not with variables. See, instead of saying W is that input. See, if this was in Java, you'd have to say the input parameter W. Java has no notion of pattern matching. So when if something is a pair, or something is a list, or something is an array, you just give it a name. Yeah, in this case, you would use a name like W for the third parameter, first parameter, second parameter, third parameter. Notice that this is not saying that there are 4 parameters. Get really careful you don't think this. This is not saying the parameters are h, g, x, and y. This function does not take 4 parameters. It takes 1, 2, 3. The third parameter has a pattern to it, and it's got 2 pieces in the pattern, but there's only 3 parameters. So they're separated by spaces here. They're separated by arrows here. Okay, the parameters are separated by arrows in the type notation, and the parameters are separated by spaces in the function definition. But there's 1, 2, 3 three parameters, just like 1, 2, 3. Okay. And I don't want to write it as 1, 2, 3 variables. ML just doesn't like that. ML prefers that when I can use a pattern, I should use a pattern. Okay. If I can use a pattern, I should. Even though this looks a little bit like a pattern, like this would be, this is not a pattern. This is just saying that G is a function that takes in C items and gives me back B type items. Okay, so that's not a pattern. Even though it kind of looks like, it might be a compound thing like this is a pattern. This compound thing is not a pattern. It's just, that's the way ML types functions. Okay, right. So that's an important thing about this example. So there's two nice things about this example. One is that there's a little bit of leeway in how you define the function, a tiny bit of leeway in what order you put these items in the output list. Okay, and then the other thing is that you see how ML really prefers that if an input parameter has a pattern, you should write the definition of the function using the pattern. Okay. Right, now let's do another one. Okay. Input function H. Oh, a list of things. Okay. Now this is going to be a little bit, I'll call it X's here, but then I'm not really using a pattern. And then here's another list of things. Oh, no, not the output is so function in, list out. Okay. Now, if I call this X's, I don't really know, like, here's what, how am I going to get a list of B's? Okay, I'm given a list of A's, and I'm given a function that if you give it an A, it gives you a B. So I've got a bunch of A's and a function that for every A I get a B, and then I want out a list of B's. So what I really probably want to do, let me write, here's the function taking in a list of A's. So I'm going to write it as in A1 and A2 and A3 and A4. So there's a list of A's going in. I'm supposed to get out a list of B's. So I'll write it this way. I want out a list of B's. Well, what B item should I put here? Well, give the function H the A1 item, and I get a B item. Give the function H the A2 item, and I get a B item. Give the function H the A3 item from the input, and I get out a B item. So this seems like this would be the most obvious way to create an output list of B items by feeding the input items, feed each input item to this function one at a time, and create an output list that way. So I really want to break this list up into pieces. So I want to think of this list as giving me an X item in front of a bunch of other items. Okay. And then I'm going to use recursion. I'm going to say, take H of the X and cons it on to F14 on the rest of the list. Apply H to the rest of the list. So now now we got to one of these things that uses recursion. Okay. None of the other ones needed recursion, but this one seems like it would be, a natural way to do this would be with recursion, because I got a list in, I want a list out. For every one of these items here, I can apply the function to it and get a B item in the output list. But I want to do that over and over again. If I want to do something over and over again, do it recursively. Do it once at the front of the list, and then tell this function to just do it again on the rest of the list. So apply that function to the rest of the list. Now, trouble is, if this is recursion, somehow I have to have a base case. So what I'm going to do is I'm going to go ahead and make this the second definition. I'm going to have I need a base case here. Okay. this will be my second case. The base case should be, what if you give me the empty list? Okay. If there are no A items, how do I cook up a list of B items? Well, if you don't give me any A items, I can only, do the obvious thing of giving you an empty list of B items. So if you give me an empty list of A items, I'll give you back an empty list of B items. I won't even use the function. Okay. So if you give me an empty list of A items, I'll give you an empty list of B items. But if you give me a non-empty list of A items written in this pattern, I'll go ahead and use the function on the first item, which gives me a B thing, and then I'll call the function recursively to get the rest of them. Okay. Okay, let's check this one. Whoops. Oh, I don't know what I pasted in there. I think my copy and paste key is still not working. So copy, paste. Oh, I got a semicolon in the wrong place. This semicolon needs to go. I had too many semicolons. Okay. Does it have the right type? It takes in a function from A's to B's, a list of A's, and gives me out a list of B's. So that's the type we wanted. Now, I can cheat on this one. I don't have to write this whole definition. This one actually has a little bit of leeway. Here's an example. I could cheat a little bit. Function F14, if you give me the function H and a list with at least one item in it. Okay, so you give me a function H, a list of A's with at least one item in it. What I'll give you out is the list with H on the one item in the list. So I'm going to give you out a list of B's, but it's always going to be length 1. So if you give me a list with one item in it, I'll give you a list with one item in it. If you give me a list with nothing in it, I'll crash. If you give me a list with more than one item in it, I'll only apply the function to the first one of them. And this has the right type. It took in a function from A to B, a list of A's, and it gave me out a list of B's. Now, I got a warning that it's not defined well because it doesn't know what to do on an empty list. On an empty list, it blows up. On a non-empty list, it only applies the function to the first item in the list. I could fix it a little bit. I can say function F14, H on the empty list is the empty list. But now I'll cheat again. F14, H on a one item or more list. If I just don't feel like writing the recursion, I can say, if you give me a list with one or more items, I will just give you the list that has H on the first item. Okay. It's still kind of, it is the right, this shows you that some of these patterns do have more than one definition. In this one, I don't have to actually process the whole list. Okay, so this function type kind of implies that if you give me a list, I should process the whole list. But I could cheat. I don't have to actually process the whole list. Now that kind of, see, that was the right, yeah. Now it doesn't worry about the empty list because I told what to do on the empty list. And I told it what to do with a list with more than one item in it, one or more items. But it only processes the first item in the list. Okay, but so this is this example here is called map. This is a very famous example. And this is the definition of map. Okay, these two examples have the type of map, but they're not really what map should do. We want map. This is one of the examples that was in the book. Map is one of the things that's talked about in this chapter. We want map to process the whole input list. We don't want it to just stop on the first item. If it stopped on the first item, it has the right type. Okay, so this type, the restriction on this type is that you pretty much have to do this. You have to take items from the input list and apply the function to them. The only choice you have is how much of the input list you want to process. Do you want to process the first couple items in the input list, or should you do the right thing and go through the whole list? So you really don't have much choice about what you do with the input items. You have to apply this function to each input item to get an item in the output list. The only choice you have is how far in this list you want to go. Okay. Here's another flaky definition of F14. Watch this one. This will be the right type. Suppose I pull off 2 items off the front, but I only apply the function to one of them. Okay, I pull 2 items off the front and apply the function to one of them. Now I'm going down by 2s, so I have to worry about hitting the 1 item case. If I hit the 1 item case, F14 with H on the 1 item case, I'll go ahead and just drop it. Okay. If you give me the empty list, I give you back the empty list. If you give me a list with item, I drop it. And if you give me a list with 2 items, I peel 2 or more items. I peel 2 of them off, apply the function to one of them, and put it back on the recursion. What does this guy do? If you think of this example here, it's kind of it's going to have the right type. Let's just check. It has the right type. Takes in a function from A to B, a list of A, and gives me back a list of B's. Has the right type. Does anybody see what it's doing? It's kind of weird. If you think in terms of this example here, what is it doing? You peel off 2 items from the input list, but you only put one thing back in, the output list. So what happens?
So you're always discarding that first element?
And what else? See, recursion now. You've discarded the first item because you peeled off 2 and only used the second one, but then you do recursion. So what happens next?
You're only doing recursion on the end of the list, or after the first 2, that is?
Yeah, that's what this does. This is the X's that are left. So you peel off 2 items, you put the function on one of them back into the output list, then you recurse on the rest of the items. But what happens when you do the recursion? Think of it as a loop. Pull 2 items out, put 1 item back in. Pull 2 items out, put 1 item back in. The recursion says, go back to the beginning, pull 2 more out, put 1 in. So the recursion says, pull 2 out, put 1 in, pull 2 out, put 1 in, pull 2 out of the input list, put 1 in the output list, pull 2 out of the input list, put 1 in the output list. So what do you end up with?
Is it is it just every other element in the original list?
Yeah, the output list is only going to look at every other element in the original list. So like in this example, it would drop A1 and have H of A2 on the output. Then it would drop A3 and have only H of, this was A4 here. See, it would only have this one and this one in the output list because it would pull off these 2, which would be YX, and use X. Then it would recurse and would pull out these 2, which would be YX, and it only used the X. So the output list in this case down here, if we think of that example there, the output list would have only H2 and H4 in it. Because pull out 2, that would be Y, that would be X, but you only put back in the X, which would be H of A2. Then you recurse. Then when you recurse, you go back around and you pull out Y and X again. But when you pull out Y and X again, you drop the Y and you only use the X, so only A4 ends up in the output, H of A4. Okay. If this had another 2 in there, if there was a A5 and A6, you would recurse a third time. The YX would be these two. A5 would be the Y, A6 would be the X, and you would end up with H of A6 in the output. Okay, so your output would be half the length of the input. And if there was a 7th item in here, that would bottom out on this base case, because you would pull 2 items out, recurse, pull 2 items out, recurse, pull 2 items out, recurse. Now there's 1 item. So you recurse on this base case. But then you just put out the empty list, so that doesn't change what's in the output. The A7 gets dropped. Okay. So this has the right type. Yeah, it has the right type. It's kind of flaky. Why would you want to ignore half of what's in the list? The key thing is that this function, what it's forced to do is apply this function to the items in this list and put the result in this list. The only choice you have is how much of this list you want to process. All of it, just 1 item, every other item. But notice that what you don't have a choice is about the only thing you could do is, given an item from this list, there's really nothing else you can do with it but apply that function to it and put the result in that list. So all these examples, they put in the output list the function applied to an item from the input list. The only real choice they have is how much of the input list to process. All of it, some of it, half of it. Okay, so this function type restricts us to a certain amount. When we apply it to the whole list, that's the map function. Okay, so this is what is famously referred to as the map function. So the map function is if you Google it, you'll get all kinds of pixie, Haskell, Python, JavaScript, Java, C++, Lisp, SQL, C#, Scala. The map function exists in every one of these languages. There's so much about it. You can read about it in any one of those languages. So like the map function in Java, okay? It's called stream map, or the map function in SQL. There's a map built, well, Spark SQL has a map function built into it. TypeScript, JavaScript, yeah. So this is the map function is this thing we just did. It's the function that takes in a function from A's to B's, a list of A's, and it's supposed to apply that function to each item in the A list and give you out a B list of the new items. Okay, so we say it transforms a list. You give it a list of A's, it transforms it into a list of B's. The map step is crucial to modern data processing. As I mentioned before, a huge amount of modern data processing is referred to as Mapreduce. Okay, so if you Google Mapreduce, what we've just seen is the map part of Mapreduce. Mapreduce is part of big data processing. It's a programming model associated with implementing for processing, generating big data sets. See, it's a programming model and associated implementation for processing and generating big data sets. The map of Mapreduce, we've just seen what it is. The reduce of Mapreduce, that's what we'll talk about in a minute. Okay, so map is this little basic thing here. This is map of Yeah, billion-dollar companies are built on this idea. Mapreduce has been the foundation for several billion-dollar companies. So it's a simple idea with profound uses because it transforms data. You give me data in one form, I map it with a function to data in some other form. Turns out that's a huge chunk of big data processing, is transforming input data into some sort of either output data or intermediate step. You know, a lot of times they do map over and over again to take input data and transform it, and then transform it, and then transform it until it's eventually in some sort of output format. And there you have these transforming functions that transform your input data into your output data. This model, this way of thinking turns out to be a great way to organize huge amounts of big data processing. Okay. All right. Okay. Let's look at there's a couple more in the examples here, but they're not the last couple examples in here aren't really generalized. Okay. So let's take this map one and see that there's a couple others that go along with it. So what we just did was this one is map. Okay. That's actually the map function. Actually, I don't need two commas. Okay. 14 is the map function. Let's look at a couple others. There's a couple functions that kind of go hand in hand with map. There's this famous collection of higher order functions. There's map, filter, fold, reduce. Okay, so let me open this. In here, I've got map, filter, and two versions of fold. We've just done map. Okay. Oh, now if you go to ML, ML has map built in. See, map was already there. We didn't need to define it. It takes in a function from A to B, a list of A's, and gives me out a list of B's. By taking that a function and applying it to each of the items in this list to produce an item in this list. So the map function is already there. Okay, so here's an example of using it. Suppose I want to map the squaring function. The squaring function, I'll write it this way. I'm going to write it in the notation that we talked about before about lambda expressions. I want the function of x that gives me back out x times x. There's the squaring function. I want to map the squaring function on the list 1, 2, 3, 4, 5. And I get out 1, 4, 9, 16, 25. See? I transformed a list of integers into its list of squares. I mapped that function and I wrote the function in this lambda expression, this anonymous function notation that we talked about last week. This is an example where this is a good example where I could use a simple little function. Like another example, if I want to map the doubling function, the function that takes every number and doubles it. Okay, so 1, 2, 3, 4, 5 comes out 2, 4, 6, 8, 10. I mapped the doubling function on my list. Here's another one. Here's a list of strings. Okay, I can map, let's see, what's a function? I could take the string dot, I think it was size. I think that's right. The string dot size function, map it on a list of strings, and I should get out a list of, whoops. Oh, dogs was missing there. Okay. I mapped now notice I didn't need the lambda expression because this function's got a name. It's the string.size function. So I'm mapping the string.size function on my list of strings and I get out a list of integers. Length 3, length 3, length 4, length 5, length 5. Okay. So sometimes I have a function with a name that I can map onto a list. Sometimes I cook up a function on the fly, like a simple little function like this. Okay, that simple function, that function, you know, it's the squaring function, but I don't need to get, it's a simple function. There's no point in me defining the squaring function and giving it a name and then applying map using the name. I can just give the formula of the function right there. Okay, and here's another example. That's a kind of weird one. The explode function takes in a list and gives you out a list of its characters. So explode on cat will give me out CAT. So when I mapped explode on this list of strings, I got out a list of lists of characters. Notice I got out a list of characters because explode, and ML figured this all out on its own. Explode produces a list of characters. So if I go back to the original definition of map, explode, this is string, this is list of characters. See, explode, string to list of characters. So this would be list of characters list. So this would be a list of characters. So I get a double list out. I get a list of characters when I use explode as the function here. And ML takes care of that on its own. That there's, see, the B here can be anything. So B could be a list of characters. So explode takes in a string and gives me out a list of characters. This was a list of strings, and this was a list of lists of characters. And there, there's CAT for cat, DOG for dog, DOGS list for dogs. See, I get out I get out a list of lists of characters. Okay. Notice I could do some this can be used to build up some pretty elaborate processing steps in a big chain of data processing, because you can take strings and breaking them up into their subcharacters. You could do all kinds of, you could take sentences and breaking them up into their list of words. So people can do all kinds of data analysis here. They could have a map function that takes in a sentence. A sentence would be, for example, a list of strings. A list of strings would be the words in a sentence. And then this could give you out something that would be like maybe the longest word in the sentence. If you're trying to figure out the complexity of, one of the ways of figuring out the complexity of text is to find the maximum words in it, or what's the average length of a word in a sentence. If it's third grade reading, the average length of a word will be 3 or 4 characters. If it's college reading, the average length of a word is usually more like 6 or 7 characters. You can judge text's level of sophistication by looking at the average length of a word in a sentence. You can use functions like these to break sentences up into pieces. People build data processing out of maps. Okay, now let's look at the next one, filter. Okay, here's what, now filter is not built into ML. It's built into a lot of languages, but it's not built into ML. Here's what filter looks like. It takes in a Boolean that you takes in a function, a Boolean valued function that takes in an A item and tells you either true or false. So for each A item, it tells you either true or false. Then you give it a list of A items, and you're supposed to get a list of A items. Okay, now, here's a dumb thing to do. Here's my function. Here's my list of A items. Here's my list of A items. Okay, that has the right, well, that won't have the right type, though. Why won't this have the right type? There's my function. There's my list of A's. There's my list of A's. Why is that not what I want? Why will that not have the right type? The answer is the same as it was earlier in the class. Earlier today, we did an example like this. What's the type of H?
SML has no clue.
Yeah, I mean, because I didn't do anything with it. So if it doesn't know what is its type, what will ML say the type of H is?
Type A?
Type A. And even this, what's it going to say this is?
A list of A's? Or just
Why
A?
would it think it's a
Or B?
list of A's? See, I didn't do anything with it. See, A item, B item, and it's returning the B item. It doesn't think there's a function. It doesn't think there's a list. Because I think it's a list, but ML doesn't, because I didn't do anything list-like with it. Now, if I did this, now it knows it's a list, because I used a pattern. And all I did here was throw away the first item in the list. So this still doesn't have the right type. This will be a list of A's, and this will be a list of A's, but what's H?
Still just type A.
Type A or B, it doesn't know what it is, so it's just going to give it. So actually what it'll do is it'll say this is a type A, and this is a list of type B's. So this will be an A, and this will be a list of B's, and it'll give me a list of B's out. Okay, you can check. What it'll do is say it's an A item. Whoops. Oh, I forgot to put the fun in front. What am I doing here?
You have two equal signs.
Oh, yeah. I didn't pay attention. I had an equal sign just sitting there here. These equal signs were those goofed me up. So filter of an H and well, this is a list because I used a pattern. So by using a pattern, I'm telling ML that that's a list. So, but this is going to be an A item. This is going to be a list of B items, and this is a list of B items. Okay. See? An A item, a list of B items, giving me out a list of B items. Doesn't know that I meant H to be a function. Okay. If I want H to be a function, I have to apply it to something. So I'm going to apply it to one of these A items. Okay. Now, does anybody see what I should do? I've got H. I've got an item from my list. I need to apply H to that item to make and I don't think it's a list, a function. So H of X. Okay. Now ML knows that H. Now ML knows that this is a list. Now ML knows that H is a function. Now, what's a reasonable way to produce an A list? Now, this is a Boolean, not an A item. It's a Boolean. Think, what could I do with this? Think broadly. If I give you a list of A's and a function that returns true or false for each one of the A's, and I want out a list of A's, what do you think I'm getting at? A list of A's, a function that returns true or false for each one of the A's, and I'm supposed to give you out a list of A's. Okay, so yeah, there's some Boolean function H and a list of A's. And I'm supposed to produce, what do you think I'm going to do? What do you think I'm getting at? What would I do with this Boolean function and these items?
Return the list of A's that returns either true or false, depending on what you want.
Okay, well, pick one. What should I do?
The ones that return true.
Yeah, keep the A items that return true. That's why it's called filter. You're filtering out the items that return false. Okay, this is it's a famous data processing step. Some choosing function on a list chooses the ones you keep. So you keep the ones that return true. So here's what I'm going to do. If h of x, then cons x on to the recursion of filter of h on the rest of the list, else what do I do? Okay, if I got true, I keep it. Else, what do I do? If h is true, keep the item by consing it on to filtering the rest of the list. If this is false, I'm not going to keep it. So what do I do over here?
Just call filter again
Call filter
with H and X's.
with h and the
X's.
rest of the list. Yeah, filter the rest of the list. So if h is true, keep that item and put it in front of the filtering of the rest of the list. Otherwise, drop that item and filter the rest of the list. Okay, so let's check this. Oh, what's my problem though?
We don't have a empty.
Yeah, I didn't do a
List
base
case.
case. I'm using recursion and I forgot to do a base case. I better, actually this is not going to work because this will recurse until it hits the empty list and it's going to have a problem. So I need to give it a base case. So filter H on an empty list. Well, if you give me an empty list, I'm supposed to filter it. It's pretty obvious I'm just going to give you out an empty list. Okay. Okay, so that's pretty easy. If I'm supposed to filter the items out of this list that don't pass this test, well, if you give me an empty list, I give you back an empty list. So filter says, here's a test, here's a test, here's a bunch of items, test each item. If it passes the test, keep it. If it doesn't pass the test, drop it and go on and test the rest of the items. Okay, so now I've got it a properly recursive function. It's got a base case. Okay, so now I don't have that error message. So it takes in a Boolean function. This Boolean function is often called a predicate. The fancy word for this guy is a predicate. Predicate's a fancy word for things that are true or false. And in fact, if you look at this definition in most books, this one won't be called H, it'll be called P. People tend to use the letter P for predicate, something that's true or false, a function that's true or false. Okay, so filter my list using this predicate. Okay, so for example, I could filter. I can keep the numbers that are positive. So function. I'm sorry. Here's my little lambda expression. Function of x returns x greater than or equal to 0. Okay, that's true for positive numbers, false for negative numbers. So filter a list of there's a list of positive and negative numbers. Filter out the negative numbers. Okay. There's my little predicate. The predicate was x goes to x greater than or equal to 0. Okay. So this is true when a number is positive. It's false when a number is negative. If I want to, I could filter out the positive numbers by just doing that. I filtered out the positive numbers and kept the negative numbers. Okay. So, I mean, this is a real powerful data processing thing. It chooses items out of a list for you. So map can, so a lot of times map and filter are combined. You might take a list and filter out things from it and then apply a function to what's left, or you might do it the other way around. Apply a function to everything in a list and then filter out the things that don't give you a certain kind of result. So filter, and so the filter function, like the map function, is going to show up in lots of functions. Well, Excel has a filter, and it's in JavaScript. It exists all over the place. Python has filter. Yeah, so the filter function exists in all. It's another. I don't know why ML. I think ML has it. I think it's in. I'm pretty sure ML has it, but I'm pretty sure it's buried in some library. I just don't know which library it's buried in. Unlike map, which is defined in the default library, I think filter is defined in some other library. And I just haven't found. I Googled for it, and I wasn't able to figure out what library it's in. I'm sure, I would think, the filter is built into ML, but on the other hand, it's such a simple function, you don't really need it built in. The only good reason why you would built in like map and filter is that if you build it into the library, you might be able to give map a more efficient version than the one we are giving it. Like if you build filter into your library, the people who write the library probably can write filter to run faster than this one does. This is probably not going to be the fastest possible version of filter. And if you want to filter lists of millions and millions of items, you'd want a fast version of filter. So map is probably in the library. And I'll bet that the definition of map in the library is not the one we wrote. It's probably somehow specialized. It's optimized to be faster. Okay. All right. So we've done map and filter. The next one, we don't have time now, but is the folds. The thing that folds are a version of reduce. So map, filter, fold, and fold is often called reduce, and map and reduce go hand in hand. Okay, so these are a little bit trickier. These two, that's what we'll do on Thursday, and that'll be the last part of what we're doing with higher order functions. The folds are tricky. Okay, folds are, we just show you. Fold is somehow a super important function in the theory of computer science. It's a universal function. So there's these famous papers on the universality of fold. It turns out you can write almost anything and you can think of in terms of fold. So we're going to talk about this. There's map and reduce and filter, but somehow the fold of this pet triple, the fold is really weird. It's a little bit trickier, and it's got a tremendous amount of power behind it. Okay, so out of map, filter, and fold, which are just ubiquitous, you'll see how many they get discussed in triples like this. Map, filter, fold, map, filter, fold, map, filter, fold. They just get talked about in combination all the time. The fold is weird. The fold has got a generality to it that's real surprising. It's more complicated than these others, and it's got, there's been interesting papers written in the theoretical literature about how you can express almost a huge number of functions can be expressed as folds, what are called folds. So it's interesting, and it's become a real cornerstone. Like I keep saying over and over again, this is becoming a cornerstone. You see how many, you Google these expressions, and you see how much people are writing about them. C#, F#, C++, Java, Python, JavaScript, all these languages are moving into this style of programming because of big data mostly. These are really good functions for doing big data. Okay, so we run over time, so let's quit. Okay, so we'll do the fold functions in class on Thursday. Okay, anybody got any questions? Now try to get the homework assignment up as soon as I can. There's going to be another homework assignment that makes use of these higher order functions. Now try to get it written up as soon as possible. Okay, so let's go ahead and quit there. And on Thursday we do folds. Okay, let's see. Stop sharing. Let's see. I clicked on the wrong button. Bye-bye.